Gibbs sampling goes is that you are going to sample this total variable vector, random vector x, which is potentially, very high dimensional, and you are going to visit every random variable inside this vector one by one, and sample that only, conditioning on the value of the other random variables, right? And we talked about a few examples. I think we quickly run through topic models, and here I want to review it again. So in topic model, we actually use two ideas. One is about Gibbs sampling. What is the other idea, if you can remind me? It is sometimes known as a collapsed Gibbs sampling. What has been collapsed? Okay, so you can see here, we have more nodes, right, more variables in the model than what we're actually sampling. So where are the other random variables gone? They are integrated out, right? So we use this trick called the Rao-Blackerization, in which we integrate out pi and beta, and then we only are left with variables which are z's. And as a result of beta and the pi being integrated out, all the z's become interdependent. Therefore, you're going to sample every z given all the other z's, right? The z's are the topic indicator of every word. And this one is proportional, as we derived, to this guy. Do you still remember what are these two components coming from? So the first guy comes from actually a distribution that is describing the likelihood of the word given the z and given, of course, the beta, right? Which are basically the hyperparameters of this topic model, right? And the second component comes from z given alpha, which is the collapsed version of the topic distribution, right? So here we should also have the b and the pi, but they are gone, right? They are integrated out. So as a result, what is this distribution? What is that distribution, if you remember? Yeah, so both of them should be a Dirichlet distribution, right? And that's why you actually come up with this form. Okay, it is the Dirichlet multinomial, and at the end of the day, you have something look like a multinomial probability, which is defined by the hyperparameters and also the actual counts, okay, in your sample. And that's basically where these two components coming from. You need to remember this. So the proposal will be in closed form, and of course, you need to normalize it properly. And then what happens is that you are going to, just form this random vector z. This is a very, very long vector touching every word in every document. And then you are going to cyclically, pick one of the z, and assuming every other z is known, you copy the other, variables, into the vector, and then you are going to sample each one conditionally on the one you just sampled from, okay, and use this equation. So at the end of the day, you are going to have a lot of such z samples, okay. This entire slide at the time t equals 2 or 3 is basically a iteration, a sample, okay, and this is the collapsed Gibbs sampling of topic model. All right, so now I left a theoretical statement about what Gibbs sampling actually is and how it is related to this bigger idea of MCMC. So here I have a one slide, very, very simple explanation of that. So the gist of this slide is that Gibbs sampling is a instance of MCMC. In fact, it is a special case of Metropolis Hastings, where you use this as the proposal distribution, okay, which is a conditional distribution of one of the random variables in the random vector given the rest of the random variables that you just sampled from. And then this acceptance rate will be guaranteed to be only 1. Okay, therefore that piece is disappeared. Therefore, this is a MH with a proposal that is always, guarantees acceptance. Okay, all right. So that's basically the justification of why Gibbs sampling is correct. And now we know 2 sampling algorithms, and I'm going to say a few words about some of the practical issues about this sampling algorithm. By the way, you guys should feel very comfortable now to go home and implement some of the sampling procedure. It is much easier than the variational and other procedures. Basically, this is almost like implementing a generative model, right? You already write down the topic model as a generative model, and you should know how to draw sample from such generative model. What you do here in the Gibbs sampling or MCMC is almost about using that generative model to generate samples. Okay, you just generate sample in a strategic way, and then you're going to get the right representation of the distribution that you want to work on. And once, of course, you have all the Z samples, for example, you can use it in different ways to calculate what is the topic distribution of every document, what is the word frequency under every topic, just by using the Z's in a smart way. Right? For example, you can collect all the Z's for a particular document, and you get a topic vector. And you can collect all the Z's corresponding to only a particular, topic, collect all the word counts, okay, under a particular number of Z, which indicates a topic. And then you have the topic-specific word frequency. So these are basically up to you to play with. I'm not going to discuss anything in detail. Here, I'm going to discuss a few important issues generic to Markov-Monte Carlo algorithms. The first one is about MCMC. So about Metropolis Hastings. So in Gibbs, you are pretty much set. You have a fixed choice of the proposal. But in MH, you actually can choose different form of Q. And what is a good Q? What is a bad Q? Right? So this is something we can talk about. And the second one, of course, is how to stop the burning process so that you can start collecting sampling. So these are the 2 very important practical issues. Many people, don't have a good sense about. For example, I many times see even professors, running MCMC. After 30 samples, they start to collect collect samples. Or maybe starting from the first sample, they start to collect samples. And then after 300 iterations, they stop. And then only come back and tell me, well, how come today I ran it, I have this result, tomorrow I ran it again, I have another result. Okay. So these are the type of questions that shouldn't happen for folks like you who took this class. Okay. We know that at least you need to have a bury-in which will take a few thousand iterations, and those samples are supposed to be discarded. Okay. And even after you bury in, when do you stop? And how do you treat those samples can be also very tricky. And let's say a few words about that. So acceptance, of course, the key criterion for judging whether a Q is good is really about acceptance rate, right? And but on the other hand, acceptance rate itself can sometimes be misleading because there is other issues about the variance. Okay, whether your sample is representative enough or not. For example, here I have 2 Qs, which actually could both be a good choice depending on really what you need. Okay, for example, this one, will give you a pretty good acceptance rate, right? Because it is really, is consistent with the shape of one of the modality in the multiple distribution very well. Therefore, once you draw sample from here, it will most likely be accepted. But what's the problem here? Well, the problem here is that the sample has a low variance, and therefore you are not having a good opportunity of exploring other domain in the space, right? So this is something you may want to worry about. If you, for example, feel that your distribution is unlikely to be a unimodal one. For example, you are really talking about a very, very heterogeneous set of data, which come from a very divergent source, and still you want to cluster it, or you want to run a topic model or stuff like that, then you should expect such a Gaussian type of distribution may not be a good idea, right? Instead this one, which is more kind of spread across, will get you a better chance of moving into different modalities, right? So this is again an art, because you don't really know the true shape of the true distribution. Therefore, you need to have a sense about exploring that. And usually in practice, what you will try is that you try a low variance one, you try a high variance one, and you start to try a few different options and see how some monitor curve or some indicator, some diagnostic statistic is behaving. And I'm going to tell you what are those diagnostic statistics. Okay, so acceptance rate. And then the other thing is about autocorrelation. That's a very interesting phenomenon, unique to MCMC. So MCMC, the reason it is called Markov chain Monte Carlo instead of just Monte Carlo is because this sequence x, 1, x2, all the way to x infinity is forming a Markov chain, okay? Meaning that the sequences are dependent. Okay, they are not IID samples from the same distribution. Okay, they are dependent samples. And when samples are dependent, what's the intuition? For example, if the second sample is just the first sample times 2, what is the intuition? They have a limited power. They really don't give you a lot of information, right? Depending, of course, on the calculation. If you are computing the average, maybe fine. Computing the angle, it depends really on what you are trying to compute. But usually, correlated samples are not very, very, very informative. And this is because of the very nature of MCMC. Therefore, you need to now also ask for the effectiveness or the effective size of the sample, okay, and how to generate samples. Maybe sometimes you get, a million samples, which makes you feel good, but maybe they are so highly correlated that you need to really, discount, their informativeness, okay, of the distribution. So here there is a way to measure that kind of correlation called autocorrelation function, which is pretty intuitive, right? So you can compute the autocorrelation in different orders. Let's assume that's order 1, for example. Let's say k equals to 1. Then it is this quantity, okay? The variance, the difference between the sample mean, over the one sample and the next sample, okay, and divided by the mean square error. And if this guy is very high, that means the next sample and the first sample are not much different from each other, right? And if k is an arbitrary integer, that means the k sample is not much different from the first sample either, right? And so you can sometimes do such a diagnosis. And usually for a, so if you suspect, such autocorrelation is the case, what do you do? Mm-hmm. Yeah, so there are two ways. You can save all the sample and discount it. But usually people don't do that because the sample can be expensive to save, right? You don't waste the storage space. So you, for example, just keep a sample every k times. Sample once, draw another 5 samples, throw them away, and then keep the fifth sample, and so on. Okay, every k times you keep a sample. So that's another trick to decrease autocorrelation. And of course, you can be more formal and compute, the size inflation factor and all that. It's still good to do that, but sometimes an experienced user may just, guess a number and do it anyway. And it is not actually atypical to draw sample every 100 iteration and keep 1. That's quite common. Okay. All right. And then there is this issue about when to stop. Okay. And so when to stop? How do we know it is convergent? That's actually a very interesting question, right? Because the theory only says that asymptotically, if you sample forever, you are going to convergent. This is simply impossible. But let's say, does a particular diagnostic statistic converging a necessary indicator of the Markov chain be converging? So that's the question I'm going to ask. So what are, first of all, those sometimes called the diagnostic statistic? What are those? It's actually, again, a kind of a dirty art. Any people can just choose some value which can reflect, the status of a Markov chain. The most kind of principled way is to compute the likelihood of the data. Okay, and that basically are taking care of all the samples you have and compute the likelihood of that. It could be a very complicated one, and you can indeed do that, but it usually gives you a pretty heavy computational burden. And sometimes you just choose some statistic from the samples or some consequence of the samples that you are trying to draw and monitor whether they change or not. For example, let's use a real example. In the topic model case, the Z, you draw a lot of Z's, right? And what are Z's are used for? If you still remember. They are used for calculating the theta or the pi and the b, right? The topic models or something. And you can just monitor maybe how much is the value of the pi or the beta is changing, right? You can monitor it, at random chosen one of them. You can measure all of them. You can measure the sum of them, anything. Basically, a function of this or maybe the function of that can all be good. You just choose an arbitrary function, okay, and see whether the value is converging. And okay, now I'm asking if this guy is converging. For example, you sample like this, typically you'll see this kind of pattern because the value is very, very oscillating. And what does that indicate if it is very oscillating at the beginning? It means the Markov chain is not reaching equilibrium yet. Okay, it is coming from whatever strange distribution. And eventually it may come to this kind of thing. It's still oscillating, but it is due to the intrinsic randomness of the sample draw, not to the lack of a equilibrium. Okay, and so I got to this point. Okay, what should I conclude? Should I conclude the chain is converging or something else? Well, it is enough to conclude the chain is converging. Any comments? So here I want you to be a little bit sophisticated about the very nature of the distribution. We talked about this fact that most of the interesting distributions are multimodal. Okay, and it is possible that your chain is such that it's stuck in this region and get sample only from this modality and still give you a stable statistic. Okay, and if you choose another MCMC, just give another random start which seats it to here maybe, then you may actually converge to different places. Okay, that's why you actually will see sometimes, this kind of behavior, this whole thing, is a very divergent. Multiple chains will lead you to a different convergence point. Okay, so in that case, that means, the convergence is not reached yet. Okay, you want to be in a status where you are in here. Okay, all the different colors correspond to different Markov chains. and they all converge to an equilibrium spot. Okay, and here you want to stop and declare the completion of the MCMC. Okay. All right. So we talked about convergence. We talked about autocorrelation, multimodality choice of proposal, and ultimately, of course, you want the MCMC to perform useful inference, and this is an example of such a useful inference. You are now really trying to do maximum likelihood estimation of model parameters, and now if you see a curve like this, which tells you that as a result of your inference, your learned model parameters cause the likelihood of data to increase, and up to maybe a conversion point, then this is like the mathematical evidence of a chain being doing the right thing. Okay, so again, I'm not saying that this is necessarily the real monitor or diagnosis statistic you want to use to monitor every chain, but eventually once you finished the diagnosis, you may want to plot this to actually show that the inference is effective. Okay. All right, with that, I think I'm going to wrap up this lecture for last Friday. You want to remember that Markov chain Monte Carlo is a adaptive sampling procedure which use a moving proposal, okay, conditioning on every new sample, and there are these two ideas underlying MCMC, and each of them give you some complementary advantage, and then there are some kind of operational tricks that you want to remember. Okay, so any question before I move on to the new lecture, which will be talking about some even more advanced topics in MCMC and Monte Carlo methods. Questions about basic MCMC? Good. If not, let me open the next one and talk about some advanced topics. Okay. There are a lot of advanced topics in MCMC. It's a very, very active area, in graphical models. And sometimes, even with the invention of a new model, people will come up with new inference algorithms for that. But here, I'm trying to maybe discuss a few reasonably generic ideas that you can use for a wide variety of models. So we'll go slowly, and we can cover as many as we can. But if we missed a few, we can either leave it to next lecture or do it offline. So recap is probably not necessary. We just recapped it already, and let's move to another idea that I want you to start getting a feel from. And this idea is very strange. So remember, we earlier said that one of the clever ideas in making MCMC very efficient is this raw Blackwellization, which means that we want to get rid of some random variables that we don't want to sample from, right? Okay, so here I'm telling you an opposite idea. I'm going to introduce some random variables, which is not necessary, but I want to sample it from, to make my sample easier. Okay, so why that's possible? This sounds like an odd idea. Okay, so this is indeed a very odd idea, but let me give you. So anybody know this idea about simulated annealing in optimization? Simulated annealing means that you want to do a optimization. Maybe sorry. Say this is a pretty hilly surface of optimization, and it's non-convex. So, and usually it is defined by maybe a exponential function of some x and over a constant, which we can call temperature. Okay, and okay, there's a negative sign there. And the idea about simulated annealing is that we assume this curve is achieved at a temperature equal to maybe something, okay, maybe tau 0. But I can also introduce another dimension where I can raise the temperature. Once I raise the temperature, you can imagine this value will become squashed to a smaller value, and somehow their contour will become flatter. Okay, just imagine I'm going that direction. And maybe over the horizon right there, moving between different valleys can be easier. Okay, that's called the simulated annealing. You just anneal it, gradually from that high temperature to low temperature, and at the same time, you move around the optimization space. Okay, and that basically is the value of that temperature. And in fact, this is an old art in, in good old day, like steel making and other weaponry making. People actually learn how to cool down a piece of hot metal in different rate to achieve different degree of hardness and stuff like that. Right? So this auxiliary variable idea is kind of related, in my opinion. I don't see such idea somehow discussed in a book, but that's my understanding. So suppose that you have this weird distribution again, which is called P, which can be very difficult to sample from. Okay, this is along the dimension of X. Okay, and once you are in here, of course, you cannot go there and so on. But now let's introduce another dimension called H, which is the auxiliary random variable. And maybe over there, with a different value of H, the shape of that maybe become a little bit more benign. And therefore, you can actually get samples in here. Okay, and so you kind of go a detour. You sample from here, you move to here by changing the H, and then you move here and you go back. And suddenly you can move into these different zooms in the distribution space. Right. So that's the value of auxiliary random variable. You use this auxiliary random variable to introduce some other dimension. It's like, if I draw a circle here and I ask you to move in a two-dimensional space, you cannot move out of that circle. But if you jump into the third dimension, you can go out of the circle. Same idea here. Right? So an extra dimension gives you sometimes a flexibility. So this is different, of course, from the collapse skip sampling or the raw polarization idea. Okay, so now let's see a few practice of this idea in many of the advanced technique that I'm going to discuss. In fact, an experienced MCMC player sometimes don't even know what's going on in the theory, but they are very, very, very fluent with using all kind of auxiliary variable trick to make sure that they can sample any way they want a complex distribution and then get convergence somewhere. Okay, so let's try a few ideas here. For example, this is an idea. It puzzled me a while, but I'm just going to give you the gist very quickly on that, and then we move to another even more kind of useful idea. So this idea is called the slice sampling. And the goal is, again, as always, in MCMC or in MC, to deal with some kind of a complex distribution P of X. Okay, this P of X is complex. Maybe it's of a weird shape. Maybe it is not necessarily normalizable or not easily normalizable. But nevertheless, I can have a P prime, which is a pre-normalized form that is easier to deal with. Okay, the usual scenario. And my goal is to come up with a procedure to allow me sample from here. Okay, so you may ask why I need this. Now that I already know metropolis Hastings, because in metropolis Hastings I used a Q, and I then sample from Q, and I use a proposal. And in the proposal, it is about P over P prime and Q prime over Q. So this normalization constant of the distribution is already cancelled. Why I need to worry about this, right? So why do I worry about this? Anybody want to give a suggestion? This is a question I asked 3 a.m. yesterday from my student, and I asked him why you care about that, because it took me a while to solve this puzzle as well, but now I know that. So in Matrop casting, you need to do this, right? So now you cancel the normalization constant, but you have a less than optimum acceptance rate, right? You need to actually throw away many of the samples, okay? So that's one thing. Then you say, okay, Gibbs sampling gives me acceptance rate 1, but in Gibbs sampling, your proposal is what? Is a P of x prime given x, which actually needs you to have the true distribution. It has to be normalized, right? So you didn't really get the good thing from the both sides of the coin, okay? So slide sampling is this idea that you want to have a 100% acceptance rate, but you don't want to deal with a normalized distribution either, okay? So in this case, you introduce an auxiliary random variable which goes like this. It's actually a kind of a interesting idea. By the way, here there are some more sentences explaining what this distribution could look like, which we actually are quite familiar with already. So here is how the algorithm goes. It goes in 2 steps. Okay. So instead of sample x, I'm going to now sample a pair, x, 8, and h. Okay, and h is my auxiliary random variable. And I actually do the following. Suppose that I started from some example already, which I had an x. Okay, now I'm going to sample, an h. Okay, according to this uniform distribution. Basically, when I have an x here, I can now always evaluate under p or p prime of x. Right? This is a pre-normalized form of the distribution. I can evaluate and get a number, right? So this number is going to define a range, okay, in which a uniform distribution is defined. And I'm going to actually sample in this range a arbitrary value, call it h. Okay, so it's here. And then once I have an h, I'm going to now draw a line here, okay, to cut through over the entire space of x to see where, my p prime of x is above that line. Okay, and for those regions which still have mass above that, I'm going to uniformly draw a sample x. So in this case, it moved me to here. Okay, so you can probably see that this strategy is nothing but a way of uniformly sample the whole region defined by the p prime of x. Okay, I'm just going to do uniform sample in this case. Okay, and the outcome is that I have a lot of x, and h, which is now populating this entire space. Okay, so this whole thing is now populated. Okay. But my goal is actually to get only x, but not x prime. Okay, so what I'm going to do is that I'm going to discard the h. In fact, statistically, you call them a marginalization, the h. But what you practically need to do is to just discard x. And magically, I'm not going to prove it, but it's easy to prove that the remaining x is actually those x's which is coming from the original distribution. Okay, it just somehow gets using this h to makes you easy to move around different regions in the px, but without necessarily computing under the original distribution, the probability of the sample. Okay, so this is called slide sampling. It's quite easy to implement, and sometimes you can even use additional trick. For example, in some cases, it might be a little bit hard to explicitly, find a h that is in which the px is greater than h. Then in that case, because we say that after we get a h, we need to draw a line and define every region where the p prime of x is greater than this h, right? And what if that's hard? If it is hard, you can use an idea called the bracketing idea. You just start from here and gradually move out and move to here and say whether on the boundary my new border is below p prime x or not. That's an evaluation problem. If it's below, you remember this point and expand a little bit more, use some kind of scheduler, right? And until you cannot move further. If you are here, then you cannot move any further. Right? So yeah, that's basically slice sampling, a very straightforward idea of using auxiliary random variables. All right. Any questions regarding this first practice of auxiliary random variable to get a more flexible sampling scheme?
Distribution is over more than one dimension.
What's that?
If you had a distribution over more than one dimension, there's still just one auxiliary variable.
Yeah. In fact, you can introduce two, but basically this auxiliary random variable, in here geographically, geometrically, I made it easy to visualize. In practice, it's any auxiliary random variable of any dimension that you introduce and use it to generate a space under the p prime that you can sample from. So it could be two-dimensional, high-dimensional, it doesn't matter. Yeah. Any other questions? If not, let's discuss another very fundamental technique, which I actually, again, spent a lot of time last night. I have to say last night I didn't have a good sleep because this whole thing was more difficult than I thought. I thought I knew the whole topic very well already, but when I actually prepared it, I suddenly found myself totally overwhelmed by some of the details. I don't know why I was very slow last night, but these details are actually worth paying attention to. Okay, so for example, this problem called reverse jump MCMC. It was actually often presented as a tricky algorithm for you to move between different model space. But I think I went through some papers and I dig out the tutorial. I think some of the key statistical insight wasn't actually discussed. So here, hopefully, we can get to that point. So remember, when we design our MCMC algorithm, we played up one important concept, which is called the detailed balance, right? So this detailed balance is the cornerstone of building guiding the choice of proper proposal distributions, right? It's either the A, which is A times Q, basically, which is acceptance rate plus proposal, or in the Gibbs sampling case, A conditional. And at the end of the day, we show they are correct because they satisfy detailed balance. Okay, right? But okay, is detailed balance the goal itself to ensure MCMC, or it is a vehicle to arrive at a more fundamental property of MCMC? That's actually an interesting question that puzzled me last night. Okay, because originally I thought, without too much deep thinking, of course, detailed balance is the goal. I want to achieve there, and then I found myself couldn't justify the practice under reverse jump MCMC because later you will see we are not using detailed balance to justify that method. Okay, so here I'm going to tell you. I will leave you this question, okay, and I will actually at least suggest you the following already. With detailed balance, an important consequence is that you can get a proof of the existence of a stationary distribution, right? What does stationary distribution mean? It means basically, it's a distribution which is invariant under transition. Right? That's stationary distribution. This is one way of understanding that. There's another way of understanding that, which is you can now take a derivative, take an integration, okay, over here. And in this case, I take integration over dx prime. And here, you take integration over dx Okay, and at the end of the day, you are going to get pi of what? X, okay, is going to be equal to pi of x prime. Okay, what does this mean? This is another way of stating the presence of a stationary distribution. It means that no matter, when you are in this stationary distribution, no matter where you come out of, you start from distribution and you make transition, you are going to arrive at the same distribution. Okay, so this is what the detailed balance or the stationary distribution is actually talking about, or equilibrium condition is talking about. You are going to arrive at the same distribution no matter where you start, as long as your sample is drawn from the stationary distribution. Okay, so that's what I copied here. And in fact, later you will see that this condition is actually more fundamental than this one. It looks like to be the consequence of this, okay? But actually, it is the goal that we want to ensure for every MCMC, and this one is the vehicle to achieve that. Okay, that's how you should understand it. And then later on, you will see we have a much better way of justifying, reverse jump MCMC. But here, let's first look at the limitation of this view. If we forgot about this, equilibrium distribution view of MCMC, but only take the detailed balance view of the MCMC, let's see what are we missing here. Okay, so in here, we basically say, there is this magic equilibrium pi, which is a distribution. By definition, you already have a distribution, which is a model. Then you are going to, stay in that model, right? And what is a model? So here, for example, I have a model which tells me there are two clusters. So it's a mixture of two models. And then pretty much you will have a distribution, pi 1, or pi 2, let's call it. Okay, and this is the equilibrium of this whole data. And your goal is to use MCMC to figure out the centroid and maybe the variance of this distribution. Right. Can you use that to do this one? I have a different model now, which now insists on 3 clusters. You cannot, right? Because this is a different distribution, right? And by definition, we say equilibrium distribution is an invariant one. You just cannot say, on here I have a 2-dimensional distribution, on here I have a 3-dimensional distribution, right? Otherwise, they are not in equilibrium. They have to converge onto one distribution. So people say that traditional MCMC isn't allowing you to explore this model selection space, where I have not only the model themselves to be estimated from a space, but also the dimension of the model, okay, can have a multiple space, okay, and I cannot really move between space. That's actually one key limitation of the traditional MCMC. So without telling you the theory, let's first visit a very smart algorithm, which actually tells you a MCMC procedure that actually allow you to simultaneously, okay, perform inference on multiple model space. This is not about modality. It is really different models. In here, I use the cluster as example, and a mixture of two Gaussian, a mixture of 3 Gaussians. But you can also imagine a HMM with 2 hidden states and another HMM with 10 hidden states, or maybe anything in the middle, right? And these are completely different models. And traditionally, people say, I need to run different MCMC to deal with different inference problem. But the reverse jump MCMC allow you to do the whole thing in a single MCMC, okay, and even allow you to assess which model is more plausible among all choices, okay. All right, so that's the idea. It allows you to actually jump between different models, for example, P1 and P2. So let's see how that can be done. This is known as a model selection, okay. So, okay. And here we're going to introduce a lot of auxiliary random variables. Okay, so we care about the original variables itself, like x is the model random variable. Okay, But in this case, because we are going to choose different models, the number of x can change. It could be a x containing 2 centroids, but could also be a x which has 3 or k centroids. So this whole x is generically a vector of unknown states that I have to estimate it. And number of states can be different. Not only the value are different, the number of states can be also different. Then I'm going to also introduce this U, which is a auxiliary random variable. Okay, it kind of allow you to perform the so-called dimensionality matching. So how can you move from a 2-dimensional model to a 3-dimensional model? Then I have this M, which is an indicator representing the index of that model, model 3 or model 2. Okay. Then I have the distribution. Okay, this is the usual one. Once we know which model you are choosing, like a mixture of 2 models, 2 Gaussians, a mixture of 3 Gaussians, you are going to have a distribution over the model parameters, x. Okay. So the reverse jump MCMC allows you now to sample this x, okay, and under condition that the M is actually switching between different number of dimensions. Okay, so and here is what is critical. We need to now introduce a few new proposal distributions, okay, over the auxiliary random variables, so that you can now have a new dimension to move, across a bigger state space. The first one is this switching kind of kernel between different model dimension, okay, from M to M prime, okay, and it should be reversible, right? You need to actually be able to jump back and forth. And the second one, okay, this is called the model proposal, by the way, and this one is called data proposal. It basically says that once you decide to move from model M to model M prime, then conditioning on your old states, what is your new states? Okay. Originally, we only have a equivalent which is a Q of x prime given x, but now we are expanding it to this quantity, which contain not only an auxiliary variable U, but also a model indicator, okay, from one to the other. And we also need to have a device which is a mapping function, okay, of the states, okay, in 2 different worlds. Okay. For example, here I have a model space, which is for 2-dimensional data, and here I have a model space which is for 3-dimensional data, a 3-dimensional model. Okay. And basically here I have a pair of mu, and then I'm going to also have a mapping function from mu to here. Okay, to allow the explicit correspondence to be established between the parameters in different model space. Okay, and why you need that, you will see actually very soon why it's going to be needed. All right, so yeah, this is, by the way, a deterministic function. It's just a bijection that you have one-to-one correspondence in this 2 model space. Okay, any question regarding the discussion so far? It's a little bit abstract. Do you want me to draw a graph to show that? Okay, let's draw a graph. Imagine I have a space. You know what a space means, right? I just put a R space, maybe R2, and here is R3, for example, right? And in R2, I have a pair of, let's forget about the U, for example. Let's just talk about the X. I have X1 and X2, right? And here suddenly I have X1, X2, and X3, because it's 3-dimensional, right? And H is just a function that maps from the first one to the second one. You may say that here I just copy this to here and copy this to here and get a new one in here that corresponds to nothing in here. Fine. Okay. But you can also have say this is actually twice the size of this one or something. Okay. Any mapping That is establishing the correspondence between the variables in two space. Okay. And now let's see. Okay, so here is already a concrete example. So let's use, for example, x1 and x2 to denote the two cluster center in a two cluster model. Okay, and then I'm going to basically draw a random value for the third cluster, and then I can easily see that the mapping function from the two-dimensional random vector to the three-dimensional one is this one, very explicit mapping. Okay. You can of course make it fancier by putting a function here as well if you want. Yeah.
Just that it should be non-random, but you pick a random one for the third dimension.
I mean, after the value of this is random, the mapping is non-random. The mapping is deterministic. Okay, I'm talking about the mapping being deterministic. The valuation, of course, this guy can be a different value as well, right? It can even add a noise or something. But the point is that this function itself is deterministic. Okay, if you have another set of values in here, you have the same mapping function. Do you see that? Okay, the randomness in here, the deterministic nature is on the function, the form of the function. Okay. All right. So we have all devices. Then let's look at a kind of a magical procedure. Okay. So you initialize like this. Say you started from some model number, maybe 2, and then you get the center of that. And you, of course, have this auxiliary random variable mu, which is so, as of now, not useful yet. You just keep it. Okay, draw a random number. And then you are going to first, propose a m prime, which hopefully moves you to the other model space. It could, of course, keep you staying here, but let's make a more interesting example. You move from 2 to 3 now. And then if you go that way, then you need to now sample a new set of mu x prime and mu prime. And then you are going to basically do the following. Okay, you are going to use the previous mapping. Actually, let's see. Yes, so you are going to now draw the new value, okay, based on the previous mapping function, right? Which involves just setting the x prime to be the x, the first two x prime to be the x, and the last one to be the mu that you just sampled from. And then, this is a proposal, and then you're going to compute a acceptance rate, okay, based on this very, very weird function, okay. And this function actually resembles what you see before in Metropolis Hastings, but it is different, okay. Okay, so you see this part. This is what? This is the ratio of model probability, right? And this is the new sample, the old sample. But note, this is different from our old Metropolis Hastings. In the old Metropolis Hastings, when you put a x of x, a p of x and p of x prime, you are assuming this p to be your equilibrium distribution, right? And therefore, this p upstairs and downstairs should look the same symbolically. They should be the same Gaussian distribution, just plug in a different value of x and x prime, right? In here, these two p are different. This is a 2 mixture model. This is a 3 mixture model. Therefore, these two are not the same distribution. Okay, so you cannot call this p a equilibrium. Okay, that's the very important difference. Whoever asked Graphical today, I want to take notes on that because I don't actually see in the textbook it's mentioned explicitly. Okay, usually in the textbook of RJ MCMC, there is no mention about what is equilibrium whatsoever. So this is not equilibrium. And then, but it looks like that. You can kind of symbolically say this corresponds to that piece. And then you have the usual thing, right? These are the proposals you use to draw new sample. So there is a ratio of the proposal from one direction to the other, and this direction to the other, and so on. Okay, quite usual. So these two are not very surprising, two proposals we use to draw the model proposal and the data proposal. And then more strangely, somehow here, there's another very strange piece. Somehow I need to put, what is this? This is called a Jacobian of the transformation matrix. Okay, transformation function taking derivative over all the things in that argument. Okay, first all derivative, and then compute a determinant of that. Okay, determinant of the Jacobian. And this is really weird. And how come this come from? This has nothing to do with our Metropolis Hastings proposals, right? But this is actually the step in your RG MCMC. And once you do that, you're going to decide whether to accept this new sample or not, and then you can repeat. Okay, so that's basically RG MCMC. Any questions so far? At least operationally, we're clear about what's happening, right? All right, so let's look at that. First, what is a absolute value of the determinant of Jacobian? Well, I assume you already know some basic calculus and linear algebra. So this is just a explicit write-out of the form. You just put this matrix, which gives you the partial derivative of this guy with respect to all the arguments in the transformation. Okay. And then you can take this basically gives you the Jacobian, and you can take a determinant of that, and you take an absolute value. Of course, in this case, you get a 1. Okay. The real puzzle is that why we need this? This is a very strange thing. We've never seen that before. Where does this come from? Okay. So here I give you some explanation, which actually leads me to think about what is really the safeguard of a MCMC procedure to be correct in the first place. Okay. And originally, many people thought it is a detail balance. Okay, it is probably not true, because if we just compute a detail balance for the RG MCMC using the proposal like this, these are proposals, we don't actually need that kind of thing. Okay, you can just put things on both sides, and in fact, you don't even have a clear picture about what is the equilibrium distribution in the explicit form. So what is actually motivating the introduction of a Jacobian under the under the detail balance is actually to achieve the correct presence of an equilibrium distribution. So basically, you are going to now use not only in this case the detail balance, because detail balance is poorly defined. You don't have actually on the one hand a transition kernel plus an equilibrium, and on the other hand another equilibrium plugged in with different value and another transition. In here you have something kind of strange. You are moving from one distribution. Okay, here it is a P over what? Over some model in a lower dimensional space, the two-dimensional space. And here you have a P prime, which still use a P, but this P is different from this P. Okay, it is a distribution over a three-dimensional space, right? Therefore, neither this and that should be called an equilibrium. Therefore, you cannot directly take a detail balance. You have to ask what detail balance is trying to achieve. It is actually to achieve the following. You want to make sure that no matter where you come out of, okay, after you make the transition, you're going to arrive at a distribution, whatever it is, that is the equilibrium distribution. Right? There should be the same distribution on the right-hand side and on the left-hand side. Therefore, on the left-hand side, you are going to integrate this whole thing with the states you come out of. Okay, so here x and the u are the states that you come out of. And on the right-hand side, you are also going to integrate over the states that you come out of. And in here, you are coming out of a different state space. Okay, it is three-dimensional. Therefore, you can see on here and here, there are two different integrals. Okay, it is integrating over different things. And that's where you need to now do one more step so that further correlation can be made explicit. So anybody know what is a change of variable, right, in calculus? Right? So this guy, x prime and u prime, is related to x and u by that mapping function just introduced. Right? Therefore, you can now replace these two with the original, with the random variable, with the variable on the left-hand side by taking the Jacobian of the transformation function, okay, and then plug in the x and the u instead of the x prime and the u prime, okay. So by doing that, what you can do now is this integration sign will gone, right? And this one is also gone, and then you can write down this equation, this equivalence, which actually gives you that justification of the acceptance ratio. See that point? Okay. So this is actually a very key step I want you to appreciate. It wasn't explained very nicely in the literature why this is true. It was sometimes explained as the requirement from detail balance. But the detail balance does not have any requirement. You can write it here, right? Basically, the detail balance is to achieve this fact, but it is not achievable with the original detail balance equation. Therefore, you are going to now actually perform the integration on both sides and see what other equivalence has to be achieved. And that's why the Jacobian is introduced. Okay, so with that, now we have this very important equivalence, and that gives rise to the new acceptance rate under RG MCMC. And then you can now move across different modality, but not different model space for a Monte Carlo. That is for MCMC, that is convergent, okay, but in different model space. All right, any questions so far? Are you still with me? This is a slightly non-trivial argument. I didn't use any any analytical proof, but I hope the highlight is somehow understood. Questions? If you don't have questions, I will have questions for you guys. No question? Okay, great. It took me a while to understand this, so that's good that you now can get it. I hope you really get it. So let me ask you the following question, which still is unanswered. So now with all this, and when we say MCMC is converging, okay, and in the classical MCMC literature, that statement was very, very explicit. We say a MCMC is converging to an equilibrium distribution, which is our target distribution, right? Which is P of X. So in this case, what do we mean by a MCMC or a RJ MCMC is converging? And converging to what? That's actually the priceless question that you want to ask yourself. Any attempt or any effort to try this? Yeah, what do we mean it is converging? And converging to what?
The new model distribution.
The new model, but it's jumping back as well. It is actually jumping back and forth between every model, right?
Joint of
okay. Joint of what?
model 1 P of X and model.
Kind of, yeah, you are kind of getting there. It is actually never made explicit in the RG MCMC literature that there is an equilibrium distribution, okay, or equilibrium distribution P of what? This is actually a mysterious thing. I don't actually know what that is. Because whenever you write a X, you lose. X kind of says you're already in one of the model space already, right? So that's the question, which I would like to leave open. But what you suggest is kind of getting there. It is actually, converging to an implicit equilibrium distribution that kind of contained all the model modality. Okay, remember that what we actually are really doing is to sample from a X and a U. And the U is the placeholder for actually many of the new kind of a center or new model component that we will use if M transition tells me to stitch to a new model. Of course, I could also remove a model if I decide to drop a component, right? So in a sense, this is our model this equilibrium space, but we never made it explicit because every time, whenever we decide a mu is to be used, okay, as a new component, say for example, M move to M plus 1, I'm going to now have x1, x2, and x3. Okay, and if M goes to M minus 1, I'm going to save x1. And then whenever we have this, we, for whatever convenience reason, we just put a P of that and P of that. Okay, and originally we have P of x1 and x2. These appear to be our target distribution, but they are actually not. Okay, they are basically a slice of our target distribution out of this whole thing, which is the target distribution of every component. We just don't use it. So implicitly, there is a distribution that contains actually x1 all the way to xk, which are the maximum number of components that you want to deal with. There is actually a distribution over that. And you are essentially reaching a equilibrium distribution in that space. But operationally, we never keep that distribution explicitly. Okay, we just keep basically every subset of that. Okay, P of x1, x2, or something. Okay, get it? Right. So this is what I believe to be what's actually happening under RJ MCMC. Therefore, there is a convergence, but this convergence is quite implicit. Okay, and the equilibrium is also quite explicit, quite implicit. Okay, with that, again, all this confusion does not hurt, prevent people from practicing it. Most people actually don't even question what is the convergence, what is equilibrium. They just sample, and once things stop changing, good, we're in the right business, and we're going to use it, right? So operationally, you can still use it. And here, I just quickly run this cluster example, and you can actually go home and figure out some of the details. So say we are going to do a sample-based solution of mixture models, and the mixture components is not fixed. Therefore, I need to have a proposal to allow me jumping between different number of components. And here, let's worry about just 3 steps: increment, decrement, and keep what it is. Okay, and then this one is going to be very simple. I'm going to just use actually use this proposal. Okay, it's pretty explicit. If I choose to go M minus 1, I'm going to just kill one cluster. Okay, I'm going to reassign every X to the remaining clusters. And if I have the same, then I'm going to still use that. By the way, there's always this mu. Okay, so the mu here, won't be used. In here, I'm going to keep it. Then what I'm going to do is that I'm going to draw a random sample, this guy, and make that to take this new value of mu. Okay, and then if I'm going to go to a higher dimensional space, add one more centroid, I'm going to use this and assign that to this new mu. Okay, so the auxiliary random variable are sometimes used and sometimes not used. Okay, and of course I need to use that very strange acceptance ratio function to decide whether this proposal should be accepted or not. Okay, and here are some specific numbers to make things more concrete. For example, I can decide with probability 2p, I'm going to stay where I am, or where I was, and then I'm going to use this 2 probability to drive me up or down. Okay, And so if, for example, I need to keep where I was, I'm going to use this proposal. Very, very explicit, right? With 1 over m, I'm going to choose just one of the cluster centroid. And then I'm going to draw the centroid from this Q distribution of mu. Okay? And this is my mapping function. Everything kept the same, except that the other one now is going to be plugged in, okay, to replace the original value. And with this, you can now compute, the Jacobian. And I think the highlight here is that everything should be diagonal other than these two, because the last one there is a swap, there is a change of the assignments, right? And you can compute. It's actually a good number. It's 1. Doesn't do anything. So that's basically the move for m equals to m, m prime equals to m. And here I have another move where I want to decrease the sample dimension, the model dimension, moving from a model of 3 clusters to another model of 2 clusters, say. Then in this case, I'm going to, again, the proposal will be 1 over m only, because you just randomly choose one cluster, kill it, okay? And you don't need to sample a new center for that. And that corresponds to another, deterministic transformation between the new centers and the old centers. You can compute the Jacobian accordingly, okay? And likewise for this incremental move, same thing. You can imagine, with probability 1, I'm going to increase another component, right? So there is no, 1 over m in front of this. I'm going to directly choose a new center from this proposed distribution and use it as the new center somewhere. Okay? All right. And I think that's it. Any questions? Any questions for RJ MCMC? So you'll see the theory example. And of course, in practice, I neglected a few things for simplicity. Here, for example, I kind of use the abstraction where I say x, c, and the u. Okay, this x is the data itself. Supposedly, you're not supposed to sample data. Data is already given, right? So what you actually care is what? So this is getting a little bit technical and deeper. So if you are going to implement this algorithm, what actual proposal you are going to use? I wrote x here just for a very generic kind of representation. But let's assume data are the actual x are the actual data points, c are the cluster centers. Then what's actually the actual variables that you want to sample from? Okay, I'll give you a hint. So again, the graphical model thing. So in the graphic model, you write down a c, you write down all the x, okay, and then we're going to say x come from this c distribution, right? But if it is really a mixture model, you actually want to introduce an indicator function z, which tells you, to which particular center this x is belonging to. Okay, so you actually want to center for every x its corresponding z, given the newly assigned c's. Okay, so these are just caveats. But again, the theory isn't really changing. There are just some technical modifications you need to do for the proposals. Okay, let's see what else. Yeah, okay. Any other questions regarding RGMCMC? If not, we have how many slides? Well, we have another 20 slides left. So we should leave it to next class, but I will just give you a hint here. There are endless issues, to actually to discuss for MCMC. And we're not going to cover all of them. Maybe next time I'm going to spend 10 minutes to address one or two more issues, but we're going to move on to new models. There are some issues nowadays becoming interesting. How to perform very large-scale MCMC, meaning that I have a lot of random variables. I have maybe a few billion random variables in a big topic models kind of problem. And then in such a big topic model, the Gibbs sampling procedure, as you can see, is by definition sequential. Right? You're going to visit every random variable one after another, okay, and until you finish the whole swipe, and then you start the second one. And this is a sequential algorithm which fundamentally prevent a parallel deployment, right? But now if you have really billions of such random variables to sample from, we ask, are there any ways to make them parallelizable, and how to parallelize them correctly, right? In fact, there are numerous algorithms published in maybe even visible places about the parallel MC, and I can tell you most of them are incorrect. Okay, you just naively put the MCMC on multiple machines and let them run without any kind of careful treatment. You don't actually know they are converging or correct converging to the right place. So in the next lecture and maybe next few lectures, I'm going to touch bases on how to do parallel MCMC in the correct fashion, okay, which allows a convergence guarantee, or at least a bound of the error that you're going to perform and produce. Okay, so that's a topic. Again, in many cases, it will involve introduction of some auxiliary random variables, but sometimes it does not. All right, let's wrap up here, and you can move on and read the rest of the slides yourself, and also start reading the Wednesday materials.